of the purple math competition. This was from April 2020 meet. Problem 11, two circles have radius 9 and one circle has radius 7. So in this picture, this has radius, these two have radius 9, then this has radius 7. Each circle is externally tangent to the other two circles, as it's evident from the figure. And each circle is internally tangent to two sides of an isosceles triangle. So this triangle here, let's call it ABC, is an isosceles triangle. It's kind of obvious here that AB is congruent to AC. As shown, the sine of the base angle of the triangle, that is this angle, or which is congruent to this one. So these angles are the base angles. The sine of this angle is m over n, where m and n are relatively prime, positive integers, find m plus n. So we're basically looking for sine of angle B. Okay, so let's draw some additional lines here. Sine of the angle is the opposite over adjacent. Clearly, the radius is perpendicular to the tangent, so we have this figure to be, this angle to be a right angle. This is a right angle, and these are the centers of the circles. And this is a bisector, which if we extend, will go through this tangential point of these two circles, and it will end at the midpoint here. Now let's connect these centers and these centers. And we know that this is 9, so is this. And this is also 9, this is 9, this is 7, this is 7, this is 9. Okay, so where is this going? So this is also 7, 7, and 9. Okay, I think we put enough angles or segments on the picture, so what's next? Let's connect these as well. Okay. Now we need to kind of connect or make sense of the sine of this angle B. Well, I wonder if we connect this point to the center, if you could somehow compute this. Well, that's the adjacent side, and we have the opposite side. This angle here is half of angle B, and you could use the trig identities compute sine of B then. So this unknown here, if we could compute it, then we're in good shape. Well, nothing pops out. You can say a lot about this angle. The connection between these angles, well, we know this is a right angle too, because this is a rectangle. This is a rectangle. All the angles are right angles. What is the connection between this angle and this angle B? Or can we compute this angle here? This angle here, because we know that angle B plus this angle over here adds up to 180. So essentially, if we could, so if we could say something about this angle, well, what do we know about this trapezoid here? So let's draw it here. So this trapezoid over here. This is 7, this is 9. And as we notice, the longer side here is 7 plus 9, 16. So this is the information we have about this trapezoid. Can we say anything about this angle? Well, yeah, we can say what the sine or cosine of that angle is. Let's go with cosine. Cosine, let's call this angle alpha. So alpha is this angle here. This is alpha. So cosine of alpha equals 2. That's 2, because 9 minus 7 is 2. Cosine of alpha is adjacent to over the hypotenuse, which is 16, equals 1 over 8. Call this one beta. And what is cosine of beta? Well, let's draw this triangle over here to see what's going on with it. This triangle has sides 16, 16, and 18. So if this angle is beta, then cosine beta equals this side, the adjacent angle beta, that's 9 over 16. So we got cosine alpha and cosine beta. So then we can compute cosine of the sum, or sine of the sum. So the formula for the sine of the sum of two angles from trigonometry is that, excuse me, sine of alpha plus beta is sine alpha times cosine beta plus sine beta times cosine alpha. And so alpha plus beta here has sine equals sine alpha. Well, you have cosine alpha. Well, then we can use a trig identity, sine squared plus cosine squared equals 1. And if I have cosine equals 1 over 8, then this is 1 over 64. And so sine squared alpha is 1 minus that, which is 63 over 64. And so sine alpha is radical 63 over 8 times cosine beta, which is 9 over 16, plus sine beta. So using the same identity descent for beta, we can compute sine beta. So sine beta is radical 1 minus cosine squared. So that's 9 over 16 squared. And therefore, that's going to be, what, over 16? 16 squared minus 9 squared. And 16 squared minus 9 squared is 16 minus 9, that is 7, times 16 plus 9, which is 25. And so that's just 5 over 16 times radical 7 times cosine alpha, which is 1 over 8. And so sine alpha plus beta then equals 248. Sorry, 8 times 80 plus 48, 128. And then on top we have 9 times radical 63. Well, actually, why can't we write radical 63 as radical 9 times radical, so 3 radical 7 plus 5 radical 7. And that's just 8 radical 7 over 128. Well, the 8's cancel out. So we got radical 7 over 16. That is the sine of the sum of these two angles. All right, so what does that have to do with sine of this angle here? Let's call this angle gamma. So there's a relationship between gamma and alpha and beta. What's going on here is that if we add, now that we named these all angles, let's call this one delta as well. So if we add alpha, beta, and delta, so alpha plus beta plus delta, that's going to be 270 because the entire thing here is 360 minus 90. That would give us 270 degrees. And gamma plus delta is 180 degrees. So by using these two equations, we can actually solve for gamma. So gamma equals 180 degrees minus delta. But delta itself is 270 minus the sum of alpha and beta. And that gives us negative 90 plus alpha plus beta. So that's the relationship between gamma and alpha plus beta. In particular, then sine of alpha plus beta is actually cosine of gamma, because the two angles, gamma and alpha plus beta, basically their difference is 90 degrees. So cosine of gamma, or I should say cosine of gamma minus 90. No, that's right. Cosine of gamma will equal sine of alpha plus beta, which is radical 7 over 16. And so sine of gamma, we're almost there, guys. It took longer than it should have. Sine of gamma then is radical 1 minus this number squared, the cosine squared, which is 7 over 16 squared. And that ends up to be an integer, okay? Hopefully it is. So it's going to be radical, I doubt this will work out. Well, is it? I'm not quick with computing things in my head, but let's just go on with the, yeah. So over 16, and in here we're going to get 16 squared minus 7. How is that an integer? Well, 16 squared is what is 256. 256 minus 7 is 249, which clearly is not a, it's not a square, because the square before 16 squared is 225. Okay, so yeah, I made a mistake somewhere. Let's quickly go over what I've done. It has to be an integer. It has to be a rational number. The sine of the angle is supposed to come out to be a rational number. So what did I do here? So 7 plus 9, 16. 7, 9, 2 over 16. That's clearly cosine of this angle. That's correct. Beta, 16, 18. Cosine of beta is 9 over 16. Okay. These both seem right. And sine of the sum, do I correctly remember this identity? I think it's, yeah. Okay, so that would be sine of alpha, which is this, yes, times cosine, which is 9 over 16, plus then we have 5 over 16. That's, where did I get 5 over 16? Where's 5 over 16 coming from? So that was supposed to be sine, oh yeah, I'm sorry. Yes, that's right. 5 radical 7. That's what we got from here. That's fine. And then times 1 over 8. That's also correct. Common denominator is 128. 5 radical. Oh, I forgot something here. Yes. Oh, I forgot this 9. Oops. This is not 3, it's 27. I'm sorry for that. That's a silly mistake. That's 32 over 128. So that's now radical 7, not over 16, but rather over 4. Okay, over 4. And so this is actually that is 7 over just 16, 16 minus 7 over 4, and that's now 9. So 3/4 algebra. Anyway, so yeah, we got 3/4. So the answer to problem 11 then is, what is m plus n? M plus n equals 7. So that's the answer to problem 11. Took longer than it should have. Let's move on to problem 12. All right, so there are two distinct pairs of positive integers, a1 less than b1 and a2 less than b2, such that both a1 plus ib1 is a complex number times b1 minus ia1, absolute value, and absolute value or the norm of a2 plus ib2 times b2 minus ia2 both equal 2020, where I is radical -1. Yep. Find a1 plus b1 plus a2 plus b2. All right, so let's see what this means when you take the norm of a complex number like this. Well, clearly we know that the complex numbers have this property that if we have z1 times z2, then the norm of the product is the product of the norms. We also know that if we have a plus ib, then the norm of a plus ib is radical a2 plus b2. So knowing these two things could give us some insight here. We get some equations. They're both equal to 2020. So if I write this as a product of the norms, and then I use this fact about the norm of a plus ib equals a squared plus b squared, then I should get the following. I should get a1 plus b1 squared, I'm sorry, a1 squared plus b1 squared radical times b1 squared plus a1 squared, that's the same thing as this one. That product should be 2020. And same thing should happen for the a2 and b2. So radical a2 squared plus b2 squared times radical b2 squared plus a2 squared is also 2020. Well, then you agree that we can actually just lift the radical and just write them as this, the equations as a1 squared plus b1 squared equals 2020, and also a2 squared plus b2 squared equals 2020. And we are looking for the sum of all these four integers, a1, b1, a2, b2. Well, that means we wrote 2020 as a sum of two integers. Can we write 2020 as a sum of two squares? I'm sorry, two squares. 2020 as a sum of two squares. Well, 2020 is divisible by 20. It's 20 times 1001, right? So 2101. So So if we could, and this itself is 5 times 4 times 101. If we could write 5 as a sum of 2 squared, which we can, just as 4 plus 1, leave the 4 out, and 101, which is clearly 100 plus 1. And then we know how to multiply. We know that if two numbers, where each of which is a sum of squares, then the product will also be a sum of squares. So I think it works like this. If we have a2 plus b2 multiplied by c2 plus d2, then that could be written as ac plus bd squared plus ad minus bc squared. That's probably best if we could use complex numbers, but anyway, so this identity is correct. You can expand both sides and notice that I get A2C2, which is, I have it here, A2D2, B2C2, and B2D2, and then the cross terms 2ABCD and minus 2ABCD cancel. So this is correct. So if I could use this fact here, this is 2 squared plus 1 squared, this is 10 squared plus 1 squared, and 4 can for now stay outside, so 4 times. Now, then this AC plus BD here would be 20 plus 1. So 21 squared plus, right, 2 times 10 plus 1 times 1. And then you have AD minus BC, or the other way, in this case, BC minus A, doesn't matter. In which case we have 10 minus 8 squared. And distributing the 4, we get 42 squared plus 16 squared. That's 2020. Can write it as the sum of 2 squares. That's one way. It looks like there must be another way. These are positive integers. Let's say this was 16 and this was 42. And there is another way. How do we find that other way? Is to probably switch up these 1 and 10 here. So let's do that. So I'm going to use the same fact, but this time use the following. Use the numbers here I had were 100. So 1 squared plus 10 squared. Does that work? No wonder. So AC plus BD then would be 12 this time. It will be 12 squared right? So AC plus BD. So 2 times 10 plus 1 times 1. That's, wait a second. So 2 times AC plus BD. So 2 times 1 plus 1 times 10. That's 12. 12 squared plus. And then we have AD minus BC. So we have 20, 2 times 10 minus 1. 20 minus 1, 20 minus 1, 19, 19 squared. And then distributing the 4, the second way to write 20 as the sum of 2 squares would be 24 squared plus 38 squared. So that could be 24, A2 could be 24, and maybe B2 is 38. And if we knew a little bit number theory, more number theory, you could say those are the only ways, but the problem also hinting that those are the only ways. So I'm gonna just go with that. And so the total sum then would be 16 plus 42 plus 24 plus 38. 6 and 4, 10, 2 and 8, 10, 10 and 10, 20, 1, 1, 3 and 4, 7, and 3, 10 and 2, 120. So we want to say that the answer to this problem is 120. Okay. Problem 13. There are relatively prime positive integers s and t such that this finite sum n equals 2 to 100 of n over n squared minus 1 over n equals s over t. Find s plus t. So we need to compute this sum. And in the competition, you're actually allowed to use a computer program, but I'm not going to try to use this by hand. If it's impossible, then we got to skip it, but let's see. So we want to add these numbers. Ooh, well, except if there is a cancellation. Oh, yeah, it is. Okay, I got it. I think I got it. Let's actually do the algebra here to see what this guy is. N over n squared minus 1 over n equals, take a common denominator. For that, you need to multiply the top and bottom here with n. So that will be n squared, and then minus. And to get the same common denominator, multiply the top and bottom with n squared minus 1. And so that's 1 over n times n squared minus 1. Okay, what does it help? Actually, maybe it's the opposite. I wanna take this and break it up. Yeah, right. So yeah, let's do the opposite. Let's write n over n squared minus 1 as the sum of two things. If you look at the denominator here, it can be factored as n minus 1 times n plus 1. So I could put 1/2 here and 1/2 here, and then I will have a correct identity. Because when I put these together again, I get 1/2 of this plus 1/2 of this. The 1/2 and negative 1/2 cancel, half n plus half n gives me n. All right, so writing this piece as this sum could help. And let's write it out. We have a summation here, so let's write it out. So that means, start with 2. That means I have 1/2 over 1 plus 1/2 over 3, 3, minus 1 over 2 plus. The next value for n is 3. So that means we have 1/2 over 2 plus 1/2 over 4 minus 1/3 plus. The next value, you just see a pattern, maybe there are cancellations. That's how usually this works out. Then we get, let's do n equals 3 as well. 1/2 over n equals, we did 3, 4. 3 plus 1/2 over 5 minus 1/4. 1/2 over, so this one is 1, 2, 3, 4. These guys are 3, 4, 5, and 6. And minus 1/5 plus. Okay, what's going on now? We have to go all the way to the last value for n is 100. So we get 1/2 over 99 plus 1/2 over 101 minus 1 over 100. Okay, I see some stuff going on here. You see, look at the denominators that have 3 in them. So we have that one, 1/2 over 3, and another 1/2 over 3, and a minus 1/3. They all go away. They cancel each other because that's 1/2 and 1/2 is 1/3, and minus 1/3 they cancel. Same happens with the ones involving, actually, so starting with, okay, we're starting with 3. Yeah, and then happens the same for 4. We have a 1/2 over 4 another 1/2 over 4, and a minus a fourth. They also cancel each other. And I can imagine that this goes on all the way to, you have to be careful toward the ends because there are certain things, like at the beginning, you see, that didn't happen for 1/2. The 1/2s didn't completely cancel out. And this one also stayed. So there is this term remaining. Let's use a different color. This term remains. This and this remain. Toward the end, we have a similar situation. So we have 1 and 2 remaining. Minus 100 remains. And this one should also remain. That means I have to write the next or the line just before the last one. So let's do that. So we get 1/2 over 98 plus 1/2 over 100 minus 1 over 99. So just like how these fractions all the way to 99 will also cancel out. This, and the previous term that involves 1/2 over 99 will go away. But what will remain would be negative 1 over 100 plus 1/2 over 100 and 1/2 over 101. So these 6 terms that I have circled here are the only terms remaining after all these cancellations. So let's now simplify it and see what that is. This is 1/2. That's minus a half. Well, obviously cancels. And then plus 1/4. So far just 1/4. Here we have plus 1 over 200. And then plus 1 over 201. And then minus 1 over 100. Gotta do some algebra and arithmetics here. So we need to combine these fractions. To begin with, I can just take care of this, put a negative here. And then a common denominator would be 200 times 201. Wait, did I have 201? No, it should be 202. Oops. 202. 202. As the common denominator, well, actually, why can't we just do 200 times 101? That makes it. That will be the right common denominator to use. 101. 1/4. 1/4 needs 50 times 101 for the common denominator. So 50 times 101 minus 101. And then here we get plus 100 because that's already 202, 100 here. Okay, so that's just minus 1. So 50/50 minus 1 over 200 times 101. So 200 times 100 is 20,000 and 200. 20,200. On top, you get 5049 over 20,200. So that's our S and T. Now we add them up to find S plus T, and these are coprime. These two numbers are relatively prime. So when you add them up, 5049, you get 49,252. That's 25,249. So 25,249 is the answer to problem 13. Quickly review this. Sometimes there's something that I overlook always. So the cancellations I believe in, only those terms remaining I believe in. 1/4 is right. minus 1 over 200 is right. Plus 1 over 202 is also right. And then you take the common denominator. Okay, 50. Yeah. All right. Okay, let's move on to problem 14. Let x be a real number such that 3 sine to the fourth x minus 2 times cosine to the sixth x is negative 17 over 25. Then 3 times cosine to the fourth x minus 2 times sine to the sixth x is m over n, where m and n are relatively prime, positive integers. Find 10m plus n. Okay. Should be a lot of trig identities that we probably can use here. What's the best way to go about this? It's intriguing. These numbers are the same. That's 3, that's 3. That's 2, that's 2. That's sine to the fourth and cosine to the fourth. This one is cosine to the fourth and sine to the sixth. So it's like as if we just switched sine and cosine. Well, why knowing one should give us the other? I mean, there's one dirty way of just really completely going go through the algebraic computations and find cosine in terms of sine and that's one way. Is there a faster way? Hmm. So essentially, this was happening. We have what's called sine S and cosine C. So we have S2 plus C2 equals 1. And then we have 3S powered by 4 minus 2C powered by 6 equals negative 17 over 25. If I solve C squared here, plug it into here, I get a cubic in terms of S. Okay, technically I should be able to solve that cubic, and that will give me S and C. I can plug into that, except that I really don't know how to solve cubic equations top of my head, and I don't want to look it up. So 3, but the unknown here is 3C to the fourth minus 2S to the sixth, question mark. Tempted to, let's call this X. I'm tempted to add these two equations and then use this along the way. Because if I add these, then I get 3 times S4 plus C4 minus 2 times S6 plus C6 equals X minus 17 over 25. And this is 3 times 1 minus the sum of S2 plus C2. So I'm using this fact that S4 plus C4 equals S2 plus C2 squared minus twice the product. So the sum is 1. So 1 minus 2 S2 C2. And these are the sum of cubes you could think of. So that's S6 plus C6, which equals S2 plus C2 powered by 3 minus 3 times S2, 3 times the product times the sum again, which is 1. So plus 2 times 1 minus 3 times S2 C2. Oh, minus 2 times. Minus. Oh, cool. Cool. So they do cancel out. So here we have, see, 3 minus 6 S2C2 minus 2 plus 6 S2C2. So the S2C2 terms cancel out. I just get 1 on this side. So X is 1 plus 17 over 25, which equals 42 over 25. Okay, so 10m plus n then is 420 plus 25, which equals 445.